Biomimetic robotic hands have incredible potential, but current thumb designs are more bulky, fragile, and complicated than the human thumb. To address this, we propose a thumb model whose state contribution to dexterous manipulation is a function of a simplified kinematic model. Hello, and welcome to this presentation on the flexure hinge-based biomimetic thumb with a rolling surface metacarpal joint, authored by Spenser Pulleyking and Joshua Schultz at the University of Tulsa's Biological Robotics Lab. To start off, we present a short video that summarizes the research in this paper.
Special thanks to Depayan Das for the design and building of the TU hand.
The motion of our biomimetic thumb's carpal-metacarpal joint takes advantage of a known relationship between two similar prolate ellipses in that they are constrained to roll without slipping when a linkage is established between their opposite foci. As a robotic joint, the linkage moves smoothly, but is constrained to 1 degree of freedom only. Our design expands this into a relationship between ellipsoids for use in a carpal-metacarpal joint. These ellipsoids are realized using inexpensive ceramic magnets. The magnetism being oriented normal to the minor ellipsoidal axes is vital to constraining the joint about its second degree of freedom, by ensuring the major axes of the ellipsoids are in the same plane throughout the range of motion. Otherwise, sublimation of the joint can occur, as seen here in a 3D printed version of our design. The ellipsoids must also be constrained to roll about their major axes, for which 3D printed flexure joints are not robust enough. To overcome this, 4 C-type flexure hinges are milled from polypropylene and are fixed to milled brass torches which encage the prolate ends of the magnets. These hinges continue to perform after more than 1,200 cycles. The metacarpal phalangeal joint is fixed as inspired by surgical arthrodesis. A motion tracking system is used to measure the excursion of points on the thumb's surface, while tendon displacement is measured via linear encoders. The tracked points represent surfaces that are involved in grasping and manipulation. To track the end effector, a 2-sensor fixture can be attached temporarily to avoid impeding the thumb from grasping objects. The relationship between tendon velocities and task space velocities is quantified by the simplified manipulability metric. The smoothness of this metric when applied to our data suggests our device is capable of fine manipulation tasks at any point in its workspace. Future work towards biomimetic dexterous manipulation will utilize this device, starting with its use in the TU hand, shown here performing select Kapanji test sequences to demonstrate its range of motion.
A little bit of background. The thumb is uniquely versatile and dexterous. It has a diverse musculoskeletal kinematics. Many different predictive models exist to try and determine the manipulability of both thumbs and of robotic manipulators in general. The manipulability metric and the manipulability ellipsoid are two of these, which were produced by Yoshikawa in 1985, and we'll talk more about how that led us to our work later on. Under-actuated devices also have fingers or thumbs that are coupled in motion of the joint, which is a constraint that could be applied to these measures of prediction of performance in a novel way. We're also looking at the biomimetic cost and complexity of doing a simplification in removing the metacarpal phalangeal joint completely. Surgical results suggest that patients have high success rates in still retaining functionality, and our previous work shows that we don't lose much volume of the workspace by getting rid of this joint. Also, in this work, we introduce a new idea, which is that the trapezium is simplified into a novel ellipsoidal joint. And so overall, our state contribution to dexterous manipulation is a function of a simplified kinematic model. So what is the bi-ellipsoidal rigid body model of the thumb CMC joint? Well, it has rigid body kinematics and 2 degrees of freedom. One is flexion of extension, and that's constrained by a magnetic returning force, which is incorporated in our prototype using magnetic ceramics. And the other is abduction-adduction, which is constrained by flexure hinges, which prevent twisting about the point of contact. This creates a no-slip condition, and we have all reversible trajectories. This retains almost all of the workspace's volume as before, with just a gimbal joint where you have simply 2 crossed orthogonal degrees of freedom. And it's made robust to damaging forces by the strength of the ceramic magnetic ellipsoids. Therefore, the thumb will just, break at the ligaments or at the, it'll essentially dislocate, which is more desirable than having a structural failure. So we have a simplification in that all of these tendons of the thumb naturally, of which there are about 12 tendons and ligaments, are reduced to 4 as a result of this simplification. So the flexure hinges as a constraint. These are used to take, as you saw in the introductory video, a interesting relationship between 2 similar prolate ellipses rolling on each other, and we make it into 3D. And then all we need is 2 flexure hinges on each side, shown in the top right, the white polypropylene. And this means that we have no slippage, subluxation, separation, or spinning about the contact point. This mimics the human thumb's carpometacarpal joint fairly well, even though the geometry, as you see on the left, is actually inverted. Those are hyperboloid surfaces, and what we have are ellipsoid surfaces. But there are definite similarities and advantages to that. So what was our experimental procedure in data collection? The goal of this, having come up with this design based on these surgical parameters, was to quantify and measure the prototype's manipulability. So we constructed this test bed also to be able to evaluate the thumb independently of any robotic hand. And so all the tendons are under a constant tension of 4.5 newtons, and the thumb is moved manually from the external forces on the Effector as if by a marionette figure. Linear encoders are used to measure the tendon displacement via a Salier logic controller, and a Paul-Hemus Liberty device is used to magnetically collect Eulerian angles and Cartesian coordinates of fixed points on the device's surface that could be used in grasping at 240 hertz. This produces a variety of point clouds, and then we want to use these point clouds to determine a relationship between the tendon displacement and the end effector position. So we completed 20 runs this way. Each run was 1 minute long, and so that meant roughly 300,000 points overall in this cloud. And we looked at which of these many possible contact points had smooth mappings between them discretely. So we can do this by constructing a Jacobian, which is a differential mapping, in this case, between the thumb's tip position and the tendon excursion. Traditional robotic Jacobians usually look between an end effector's tip position and the joint angles. But in this case, we're directly controlling not the joint angles, but the tendon displacement and incursion, because this is an under-actuated device. So this actually gives an advantage in terms of simplified controllers. So over these points, we then essentially bypass the joint space and go from tendon space to task space with this Jacobian. And the way we located that tip precisely was essentially just using CAD geometry about the center of the thumb tip's pulse. So what is the simplified manipulability metric that we express the results of this relationship with? So this new metric represents a scalar quantity which describes the variance of a tendon movement velocity relative to the end effector movement velocity through its workspace and time, as represented by Cartesian coordinates. With this, we can deduce what region of the workspace might be the best region to operate within, because the tendon length does not appear to fluctuate wildly there for small displacements and vice versa. So this is essentially a simplified form of the full numerical Jacobian between the tendon excursion and the end effector positions, but instead of searching locally in all possible directions within the full data set, it's only computed backwards and forwards along the path taken as the data was collected. So estimating the full Jacobian is much more numerically intensive, but not expected to be drastically more accurate. This metric, however, represents how well conditioned the mapping is between the controlled tendon output position and the more dynamic elements like the end effector position and the position of various surfaces on the thumb. So we normalized the value of the simplified manipulability metric to get this graphic, and we can see that there's no general region with high values, although there's some small values that are raised, and that may be due to catch points, where essentially as the under-actuated mechanism moves through space, the tendons are catching on objects or something and experiencing hysteresis. Overall, this indicates that there is very little relative change of the velocities of the tendon to end effector path, which suggests that a smooth, well-conditioned mapping does exist. Prototype and installation, we put this into the TU hand, and all of the parts are extremely low cost. We have flexure hinges enabling the first degree of freedom, milled brass torches enabling the second degree of freedom as those ellipsoids are allowed to rotate, and then the metacarpophalangeal joint is fused as a hollow carbon fiber hole, and mechanical stops limit the joint. In conclusion, we designed a bi-ellipsoidal model of the thumb CMC joint based on a simplified kinematic model. We incorporated flexure hinges into this and came up with a metric to qualify the relationship between task space position input and tendon output for future robotic control. Now the design is being implemented into the future robotic hands, starting with the under-actuated biomimetic TU hand.
To learn more, please visit our lab's website, and if you have any questions, feel free to get in touch via this presentation Slack channel or email me at the address below. Thanks for watching.